In today's lesson, we're going to talk about something called a logarithm. So we're going to learn what are logarithms, how are they evaluated, and how can they be useful to us. So let's say we have this equation 2 to the x power equals 8. And so whenever you're solving an equation, you're trying to figure out what is x. Well, I could probably do this in my head and say, well, I know that 2 to the third power is 8, so x must be 3. So one way I can solve this, solve it in my head. But kind of changes if I have something like if I have the equation 2 to the x power equals 15. Then if I try to solve this in my head, kind of stuck. Now I could kind of reason my way through it. I could say, well, I know that 2 cubed is 8, and I know 2 to the fourth is 16. So I'm going to guess, since 15 is really close to 16, I can guess that x is probably like maybe 3.9-ish, because it's really close. I'm going to guess that's what x is, but I can't be for sure. So I'm going to need a mathematical operation to solve for this x. So what I can use is something called a logarithm. A logarithm is an exponent. So one thing to know, logs are exponents. And that we can use them to help us solve for an exponent. So we'll have to switch back and forth between the exponential and the log form of the same equation. Not the inverse of the same equation. So if we have an equation that's given in exponential form, I can translate that equation into log form by following this pattern. Notice, let me grab a highlighter here, that I have this base a. That's the base on the log. The exponent, b, is what you would set that log expression equal to. And then c is called the result. So log with the base of the result is equal to the exponent. Now, I like to think of this in this motion like a raised to the b is equal to c. I like to think of it in a circular motion, or I know that bases are going to be the same number, and then the exponent is what it equals. So we'll practice. We'll have to translate back and forth between log and exponential form with the next examples. So if we look at example 1, we need to know what is the logarithmic form of y equals x to the 8th. So I am going to copy this. No, I don't. Okay, so I'm going to say, okay, y equals 8 to the x. So I'm going to try to write it in log form. I know that the bases are the same. So log base 8 means I'm going to write log base 8 of y equals the exponent. So the bases are the same. The exponent is what we set the log expression equal to. And then the y is what we're taking the log base 8 of. Let's do a couple more. Example 2, we're converting back and forth between log and exponential forms. So what's the log form of 7 to the third power equals 343? Well, let's try it. I'm going to write log, the base is going to be 7, of this number 343 equals 3. So once again, I'll grab my highlighter. The basis, whoops, I don't want that color. There we go. 7's the base, so it's the base on the logarithm. 343 is the result, so that goes right there. And then the exponent 3 is what we set the log expression equal to. We'll also have to work the other way. Log base 4 of 16 equals 2. Oh, I'm recopying the problem. I need to change that to exponential form. So what is the base? Well, the base is going to be 4. This 2 is going to be the exponent. And 4 squared is in fact equal to 16. So that's the exponential form. Now in example 3, we're going to have to evaluate it. So they want to know what is the value of log base 3 of 1 over 81. And we want to do this without our calculator. So what I like to do is I like to say log base 3 of 1 over 81 is equal to x. And then I'm going to rewrite in exponential form. Rewrite that in exponential form. And exponential form, the base is 3. X would be the exponent, equal to 1 over 81. Then I'm going to have to solve. So once I've rewritten in exponential form, the next thing I want to do is I want to try to write it so that both sides of the equation have the same base. So let's come over here. Try to write the equation so that both sides have the same base. That means I want both sides to have a base of 3. So the left side I'm going to leave as 3 to the x. And 81, I'm going to try to write as a power of 3. Well, I know that 81 is the same as 3 to the 4th power. And I'm close to having both sides written to the same base. However, the 3's in the denominator. But if I want to write this as 3 to a power, 3 to the x is equal to 3. And 1 over 3 to the 4th is the same as 3 to the negative 4th. So now I can see just from inspection, 3 to the x equals 3 to the negative 4. That tells me that x equals negative 4. And then in part B, let's try part B, log base 7 of negative 7. First of all, number 1, rewrite in exponential form. So I'm going to abbreviate that exp form. So we're going to say that equals x. So 7 to the x power equals negative 7. And then step 2, I'm going to try to write so that both sides have the same base. All right, so I've got 7 to the x. Now, can I write negative 7 so that it has a 7? Yeah, it's already a 7. I mean, I could write so that this negative is out here, but I want to have the same base with the same exponent. That's not really happening. So then I'm trying to think, okay, well, is there a way I can solve this by inspection? Is there any number that x could be in order for 7 raised to that number to be negative 7? Well, 7 to the first power is 7. Okay, that's not negative 7. What about negative 1? 7 to the negative 1 is 1 over 7, which is not negative 7. 7 to the 0 is 1. There's nothing I can raise 7 to in order to get negative 7. So this expression would be undefined. And it's undefined because no value of x would give an expression equal to negative 7. We'll do a couple more of these. I believe your workbook might have a third example in there. C, log base 5 of 5 to the 9th power. So I'm going to set that equal to x and try to solve. So write it in exponential form. 5 to the x power equals 5 to the 9th. And by inspection, I can see that x equals 9. Here's a few more extra examples. Let's say I have log base 5 of 125, and I want to know what that equals. So I'm going to say that it equals x. And this is an extra example, by the way, so we'll call this example D. Exponential form would be 5 to the x equals 125. And if I try to write it with the same base, I know 125 is the same as 5 to the 3rd, so x would be 3. Let's see, a couple others you need to see. We'll call this example E. Log base 3 of 0. 3 to x would be 0. Is there anything x could be to be 0? Nope. So we'll say this expression is undefined. And then maybe one more example F. Log base 1/4 of 16. So if I change it to exponential form, 1/4 to the x is equal to 16. And I see the 4, I see 16, that makes me think of 4 squared. So I'm going to try to write both of these with a base of 4. So 1/4 is the same as 4 to the negative 1. And that x, I still need to bring it down as an exponent. 16 is the same as 4 squared. So on the left, we multiply these exponents. I get 4 to the negative x equals 4 squared. And I can set up the equation negative x equals 2. So x would be negative 2. Now, in addition to the log bases, all the logs with the subscript, that base at the bottom, we also have what's called a common log. We have a common log and a natural log. If the logarithm has base 10, so if it had log base 10 of x, it's called a common log, and the base of 10 is implied, and we write it as just log of x. So if you don't see a base written, the base is always 10. The other common log with a base e is called the natural log, and we write it as ln. Note, make a note to yourself. This is an L, ln of x. And so the expression log base 10 of x and log x, these mean the same thing. And then natural log base e of x and ln of x also mean the same thing. And usually you won't see this written there because the e is already implied to be there. So you won't see that e written. Okay, so let's try a couple of examples. So example 4, what's the value of each logarithm expression to the nearest 10,000th? So log of 321 means log base 10 of 321. And now if I were to try to evaluate this, I could set it equal to x and say 10 to the x equals 321 and I notice, okay, I don't know in my head what x could be, and I also can't change 321 to have a base of a 10. So instead, I'm going to go to my calculator and I'm going to type in log of 321. Now in Desmos, I can just type in the word log of 321. And the number is automatically generated for me. It says to the nearest 10,000th, which would be, let's see, tens, hundreds, thousandth, 10,000ths. That would be 4 decimal places. So I would say 2.5065. So over here, I'm going to say that, where's my eraser? I'm going to say that this is approximately 5065. Now for natural log, I can just grab my calculator. I can type in ln. Make sure you type in an L, not an I, an L of 1215. and I see that it's 7.1024. You can do the same with log of 0.7, 0.17, and so on. We also have to solve equations with logarithms. Now these are some pretty straight, log equations can get pretty complicated, but for right now, we're going to keep it straightforward. And the approach that we're going to use with these types of equations is if you're given a log equation and you can't just come up with an answer, the first thing you're going to try to do is you're going to try to translate it to exponential form. So here I see my equation as log of 3x minus 2 equals 2. The base is not written there, but I understand that it's a 10. So I can write the equation 10 to the second power equals 3x plus 3x minus 2. And then from here, I have a really simple equation. So 10 squared is 100 equals 3x minus 2. If I add 2 to both sides, I get 102 equals 3x. Divide both sides by 3, and 102 over 3 is equal to x. And they tell me to round to the nearest thousandth, which is 3 decimal places. So 102 divided by 3 is 34. 34 even, so I don't even have to round. Part B is e to the x plus 2 equals 8. Now the equation before it was in log form, so I translated it to exponential. If you're given an equation in exponential form and you can't solve it the way that it is written, you can translate it into log form. Maybe that will help you solve. And I also notice that I have an e as a base. So since e is the base, that tells me I'm going to use the natural log. And I'll draw a cursive L so that I don't confuse it with a 1. So I'm going to change it to log form. So if I change it to log form, I'll have the natural log base e of 8 equals x plus 2. Now the natural log base e is already understood, so that's the same thing as natural log of 8 equals x plus 2. And so the natural log of 8 itself is a number, so it has parentheses around it, and it itself is one number. I need to get the x by itself, so I'm going to subtract 2 on both sides. But I can't subtract the 2 from the 8 because the 8 is the natural log is being taken of 8 first, and then I'm going to subtract from 2. So the natural log of 8, close parentheses, minus 2 is equal to x. So x is approximately, if I grab my calculator, actually this is the exact form. This is the exact answer. So sometimes you'll have to enter your exact answer, and then if I find out the decimal approximation, I'll just grab Desmos and type in the natural log of 8. You'll see there's no parentheses here, so I want to put parentheses around the 8 and then subtract 2. So about 0.079. And they told me to round to the nearest thousandth, so that's 3 decimal places. So x is approximately 0.079. This is what we call the approximate answer. I left an approximate answer. So that should do it for our lesson today. Have a great day and have fun with these logs.